Welcome everyone again to the second part of the talk or the tutorial that Aaron Wagner is presenting on feedback communication. Last time I enjoyed his summary of the work that is in the literature. I mean, especially the 4 ways feedback communication can help. I think it was 4 ways, right?
5.
5, sorry, I missed one. And I think today, Aaron want to dig more into the part that he did on feedback communications. So the stage is yours, Aaron.
All right. Thank you, Salim. It's a pleasure. So yeah, Wednesday's talk was more of a tutorial or a survey about what was classically known, and this is more of a conventional research seminar on some more relatively new results. And I'll be presenting joint work with 2 of my past students, Nirmal Shende, Ujjal Altu. All right, so yeah, so the tutorial on Wednesday, as Salim mentioned, sort of went through kind of the list of qualitatively different mechanisms by which feedback is useful in communications. In fact, we kind of restricted the scope a bit and just said within the context of block coding, in what ways is feedback useful for improving the performance? And we cataloged a list. There were 5 items in the list. So first of all, I said if the channel has memory, then you can use the feedback to predict the future. And that's useful. If the channel is unknown, you can use feedback to learn the distribution or learn the law. And that's useful. If the coding time is not fixed, like you have some flexibility in when you decode, then you can kind of decode early or later opportunistically, depending on the channel realization, and you can get gains there. Likewise, if you have some average cost constraint, like a power constraint, you can use power opportunistically. So kind of steal power from the good realizations and then, deploy it on the bad realizations, and you get a net gain from that. And then kind of more technically, in the low rate regime, you can get an effective minimum distance increase using feedback, and that gives you a performance gain as well. All right, so as I mentioned on Monday, if you broaden the scope and look beyond block coding and point-to-point channels, okay, then there are lots of other ways where feedback is useful. Okay, so if you're in networks, okay, that opens up a whole host of ways of using feedback. If you're interested in control as opposed to just sending messages back and forth, okay, that opens up new ways. Streaming codes. Okay, so I don't want to imply that this is like the complete list. It's more like just in this very narrow context here, performance of block coding over point-to-point channels, where this is kind of the list. And that's going to be our focus here today, just as it was on Wednesday. So we're going to ignore all those items. All right, so the question I'd like to address today is, this is the list from Wednesday, the list of mechanisms. All of these mechanisms are sort of classically known. They date back to the 50s, 60s, and 70s. The question I'd like to ask is this it? Okay, is this like the complete list, or are there other ways of using feedback in this context that have just yet to be uncovered? Okay, and it's obviously not a completely well-posed question, right? Like you can never really answer this definitively in the negative, okay? Because you can always, come up with ways of changing the model in ways that allow feedback to be useful in new ways. For instance, if no one had ever thought about variable block length coding, okay, then our list might have 4 items in it, and then we might say that's it, and then someone comes along and says, well, you can decode opportunistically, right, early or late, and then that would add a new item to the list. So you can never really definitively say this is the complete list. And of course, there's some question as to how distinct are these things. As we discussed on Wednesday, the first 2 items are kind of related. Third and fourth items are kind of related. But nonetheless, I think it is a worthwhile question to consider. And one way of making it well posed is to consider a model in which we just assume away all 5 of these mechanisms and then just see if we can either prove that feedback is not useful or come up with some way of using feedback, which is then presumably different from all 5 of these things. Okay, and that's exactly what we'll do. Okay, so we'll consider a model, point-to-point, block coding, communication. There's for a channel with no memory, known distribution, fixed decoding time, no cost constraint, high rate regime, okay, and then see whether feedback helps, okay. And the punchline is it does help, okay, and there's like a new way of using feedback that's kind of different from this group of 5, okay, where that crops up in that model. All right. So here is the model. It's the same notation from Wednesday. So this is, about as vanilla of a model as it gets. Okay, so it's a DMC. Let's start without feedback. So the input alphabet is X, the output alphabet is Y. We'll call the channel matrix W, just a stochastic matrix. Okay, so the encoder takes a message, we'll say k bits, outputs n channel inputs, the channel maps that to n channel outputs, and the decoder observes those and tries to guess the message. The feedback version is just that the encoder can choose x2 after seeing y1 and x3 after observing y1 and y2 and so on. So just, same as Wednesday, very basic setup. Okay, and as I mentioned on Wednesday, real feedback out in the world is never so ideal, right? This is a noisy channel itself, just like the forward link, but this is the context that we'll consider feedback here. Okay, so the figures of merit that we'll consider, there's the number of bits you're sending, there's the amount of time you're using the channel, there's the rate, the ratio of the two, and there's the error probability. And we'll consider the block error probability, assuming that the U's are IAD Bernoulli half. Okay, so pretty basic setup. It's hard to get more basic than this. Okay, so we're going to consider an asymptotic performance metric. I talked about various asymptotic performance metrics on Wednesday, right? So there's error exponent, there's capacity first of all, and then there's error exponents, there's the second order coding rate, there's the moderate deviations performance. And we're going to focus on the second order coding rate here. That's the highest rate of the bunch. Okay, so if you go back to Wednesday's talk and review the talk or look at the slides, the second order coding rate is the one that involves the rate approaching capacity the fastest and the error probability falling off the slowest. In fact, it's not falling off at all in this asymptotic regime. Okay, so if we're interested in high rate asymptotics, like this is the regime to consider. That's what we'll do. Okay, so some notation. So given a block length n and an error probability epsilon, I can ask for the largest rate over all codes with this block length and this error probability. I can do that with and without feedback. Okay, and both of these quantities approach capacity as n tends to infinity for fixed epsilon. Okay, so that's basically saying that feedback does not improve the capacity. So that goes way back to Shannon in the 50s, Dobrushin also in the 50s. Of course, Shannon didn't state the result quite this way in 56, but same idea. Okay, the second order coding rate basically captures the speed of convergence in this limit here. Okay, so it turns out both with and without feedback, the back off from capacity is order 1 over square root of n. And so we define the second order coding rate to be the constant in the back off. Okay, so second order coding rates defined both with and without feedback, just as this R quantity, this maximum rate with the capacity subtracted off times square root of n to pull out that constant. Okay, so second order coding rate sort of governing how fast you're approaching capacity as the block length tends to infinity for fixed error probability. And that's the asymptotic regime that we will consider in this talk. Okay, so does feedback help in this regime? So we've set up a model where we kind of assumed away all the kind of classically known mechanisms where feedback is useful. And now we want to know, will this feedback help here? Or can we just prove that it doesn't? So as with Wednesday's talk, we'll start with a negative result. Okay, so it turns out for symmetric channels, the second order coding rate's not improved with feedback. So these two beta quantities are the same with and without feedback. Okay, this is proved by Polyansky et al. 2011, and the non-feedback case was earlier characterized by Strassen in 62. And I defined symmetric channels on Wednesday. Let's do it again for good measure. Oh, by the way, this is a stronger notion of symmetry than's really needed to prove this result. Okay, so I'm a bit understating the theorem here of Polyansky et al., but it's it gets the point across. Okay, so this is the kind of standard definition of symmetric channels. It's from Cover and Thomas, or it's the one used in Cover and Thomas anyway. So define a channel to be symmetric if, when you view it as a stochastic matrix, you can partition the columns, namely the outputs, in such a way that within each partition, the columns and the rows are all permutations of each other. Okay, so here's the BEC as a matrix, right? 2 inputs, 3 outputs. I can partition it like this, right? And then within this partition, the rows and columns are, the rows are permutation of each other and the columns are permutations of each other. And likewise here, there's only one column, right? Not every channel is symmetric. Okay, so for symmetric channels, the second order coding rate is not improved. And in fact, you can say more, and I alluded to this on Wednesday. So for symmetric channels, feedback does not improve the second order coding rate. It also doesn't improve the error exponent for large rates. It doesn't improve the order of the polynomial prefactor in front of the error exponent for large rates. It doesn't improve the third order coding rate. Okay, so this is the second order coding rate. You can look at the next term in the expansion. So you have capacity plus 1 over square root of n plus something. Okay, and that something is also not improved with feedback. The moderate deviations performance also not improved with feedback for symmetric channels. So for symmetric channels, pretty much every asymptotic performance measure that we can compute shows no improvement with feedback versus without. So that leaves asymmetric channels. For asymmetric channels, as mentioned on Wednesday, the high rate error exponent is not improved by feedback. Okay, so this does not look promising at this point, right? But in fact, we will show that the second order coding rate can be improved by feedback for some asymmetric channels, okay, using a mechanism that, at least to my mind, is qualitatively different from the classical 5 that we described on Wednesday, okay? So that's the kind of the takeaway of the talk. So let me describe the mechanism, and I can describe the basic idea quite simply using a little coin puzzle, okay? So suppose you have 2 coins, you have one in each hand, and this is a picture of my own hand I took this morning, so it's got the same shirt sleeve in it. So suppose you flip coins, and if you can flip either one. If you flip the one in your left hand, you get $1 if it comes up heads, and you lose $1 if it comes up tails. And the coin on the right is the same, except you get $2 if it comes up heads, and you lose $2 if it comes up tails. Okay, so both coins kind of give you a zero mean return. Okay, but the spread is different. And both are fair, okay, and like that they're fair going in, so there's no exploitation trade-off here. You're not trying to learn the distributions from flipping, okay? You know they're both fair. You're just deciding how much to wager, okay, on each flip. All right, so here are the rules of the game. So you start with $0. You're going to flip some coin n times, and you can potentially swap coins, or flip one and then flip the other. It doesn't have to be the same coin all the way through. The goal is to minimize the chance your final wealth is below alpha, where alpha might be positive or it might be negative. Okay, and the question is, what are the right strategies here? And also, does feedback help? And by feedback in this context, I mean adjusting the coin that you're flipping, or changing coins midstream, depending on how you're doing. Okay, so the non-feedback version of this is, at time 0, you just declare which coin you're going to flip on each of the n time steps. Feedback means that you can kind of see how things are going and then kind of switch coins midway through as frequently as you want if you find that advantageous. So what are the strategies that are good, and does feedback help? Okay. So, at first blush, it's tempting to think that doesn't make any difference, right? Because both coins are zero mean. So, if you think just in terms of expectation, it makes no difference which coin you flip. Okay, but this thing is scored not in terms of expectation. It's this threshold behavior, right? So pictorially, you start at 0. You have this threshold at alpha. Here, alpha is negative. Okay, and you flip, and so you have like this random walk, right? And each time step, you're either taking a step up or down of size 1, or a step up or down of size 2. And you don't control whether it's up or down, that's random, but you control whether it's 1 or 2, okay? And you want to minimize the chance that you fall in the shaded region here, below alpha at time n. So you want to avoid that region. You want to end up here. All right, so what are the strategies? So let's start without feedback, that's simpler. Okay, so suppose alpha is negative, so you start above the threshold. Okay, all right, so it's all zero mean, right? Like, I mean, the returns are, you start with 0 and the returns are zero mean. Okay, so your expected wealth at time n is 0. All right, and that is above the threshold, right? So you're kind of expecting to win, right? And so as such, the way to minimize the chance of falling below the threshold here is to concentrate the probability as much as possible around the mean, right? You want thin tails, okay, to minimize this tail probability, right? So it makes sense to flip the +1, -1 coin the whole time, right? That gives you the least amount of mass down here. So play timid, right? Play the timid coin, or make the timid bet. All right, conversely, if alpha is positive, okay, then on some level you're expecting to lose, right? Like you're starting with $0, you're expecting to end with $0, and you want to minimize the chance that you fall below alpha, and 0 is below alpha. So the way to minimize the probability of the shaded region is to actually like increase the spread as much as possible, like fatten the tails as much as possible to throw as much probability as you can up above alpha, right? So you should play bold in this case, right? Play the +2, -2 coin the entire time to kind of fatten these tails. All right, what about feedback? So let's start with the single change point situation. So suppose you pick one coin and you flip that n/2 times, and then at time n/2 you can decide whether to switch or not, and you then flip the same coin that you've picked for the remaining n/2 time periods. So what are the right strategies? So at time n/2 it's sort of the same problem, right? It's just you have half the time horizon. So play timid if you're above the threshold, play bold if you're below. What do you do at time 0? So this is kind of an instance of the same problem. It's just that your final, your objective here is not this like 0-1 discontinuous reward or cost that you have here. You have some kind of cost to go, induced by this second step, but it's natural to, again, play timid if you're above and play bold if you're below. And more generally, a reasonable strategy is to just at each time step, flip the +1, -1 coin if you're above the threshold, and flip the +2, -2 coin if you're below. Like play timid when you're winning and play bold when you're losing. If there was a coin that had 0, 0, right? Like you get $0 if you win and lose $0 if you lose. Like you'd play that whenever you're above, right? You just lock in your current state. And you can't do that, but +1, -1 is as close as you can get. All right. And one takeaway from this is that with feedback, you can do better. Okay. So with feedback, you can, adjust your strategy. And when you fall below the threshold, you play bold and get more variance and so on. So you can do better than if you just play one coin the whole time through. Okay. Just as an aside, just as like a fun aside, I don't know if people are familiar with the 538 website. It was in the news recently. It's known mainly for its political forecast, like election forecast, but they have a puzzle column. Okay. And this past February, they have a weekly puzzle column, and for February 21st, 2020, the puzzle was like exactly this coin flipping thing. I had nothing to do with it. It came from somewhere else. I don't necessarily claim that this puzzle is novel. Okay, it's just relevant to our coding problem. And I was actually working on the final version of the journal paper, and I went to take a break, and I go to the 538 website and I click on their puzzle, thinking I'd get something different to think about, and like lo and behold, it's like exactly the puzzle that is in our paper. So.
This is
anyway,
right, Aaron? It used to be in New York Times, right?
Beg your pardon?
Is it like Nate Silver's website?
That's right. Yes, this is founded by Nate Silver, who is the editor-in-chief, and it was part of the New York Times website for a while, and then it kind of moved around. It was part of ESPN, and now it's part of ABC. As you can see up here. Yeah. Good. So to use this, we actually need a continuous time version of the setup. Okay, so we're going to do a little bit of stochastic calculus here. Just think of it as a continuous time version of the random walk puzzle we just talked about. So let B be a standard Brownian motion, and consider this controlled diffusion, where you essentially control the instantaneous variance of the Brownian motion over a range. Okay, so again, just think of it as a continuous time version of the discrete time random walk, if you like. And the question is, how do you choose the controller here that controls the variance to minimize the chance that this diffusion ends up below alpha at time 1? And it starts at 0. Okay. There is a very clean theorem that describes the optimal controller due to McNamara in 1983. And he showed that the optimal controller is bang, bang. It switches between either using the minimum variance or the maximum variance, depending on whether you are above or below the threshold. Okay, so you play maximally timid or maximally bold, depending on whether you are above or below the threshold. You never use any of the intermediate variances which are available to you. It's not optimal to do that. Okay, so this is what it looks like in simulation. Okay, so the idea is whenever you fall below the threshold, you sort of like blow up the variance, to try to like make things happen quickly and get out of that bad state. And then whenever you're above the threshold, you try to cool things down, okay, and get it to move slowly so you don't end up back below the threshold, which is where you don't want to be. And that's the optimum strategy in the continuous time limit. All right, so I promised hockey, hockey teams and foraging animals, right? So, once you see this theorem, it kind of dawns on you that actually this phenomenon, exists all over the place. So there's nothing special about hockey. I mean, most sports have, some notion of this, but it's, here's the hockey example, right? So if a hockey team is behind by many goals late in a game, then they replace their goalie with an extra offensive player. Okay. And this is a very risky strategy, right? But they're expecting to lose. Okay. So if they play it safe, they're almost certainly going to lose. So you replace your goalie with an extra offensive player, your goal is wide open, it's potentially easy for the other team to score, but it's also easier for you to score because you have an extra player out there, right? And other sports have similar notions, right? There's a Hail Mary pass in American football. There's the notion of playing the infield in baseball, et cetera. So most sports have some notion of this. McNamara himself was in part motivated by mathematical ecology. So he studied questions in ecology and modeling predator-prey situations and stuff. And he pointed out that there were papers established that animals near starvation engaged in risky foraging strategies, whereas animals that were not near starvation, engaged in less risky or more timid foraging strategies. That was part of his motivation for proving that theorem, was to try to explain that finding in the ecology literature. Okay, so that's all good fun. So let's apply this to coding now. So yes, please.
So can we ask an interesting question in your example of the two coin of, if I get to choose between two games with different n and different alphas, can I tell which game would be more beneficial for me? I'm interested to see if there's something interesting between alpha and n, what would be the block length?
Between alpha and n, in the discrete time version?
Yeah.
Okay, so what's the question?
So if I'm just trying to think how n enters the picture. So if I'm given two games with same coins, but different alphas and different n's.
Mm-hmm.
Is it clear? It's clear which game is going to be more beneficial or more.
You're asking which game has the larger gain from having feedback? Is that the question? Or just which one has the overall better probability of winning?
Yeah, I guess. Yeah, which one has better probability?
So, okay, I mean, I guess, I don't have an optimality result for the discrete time version. I mean, we have an optimality result from the continuous time version.
Okay.
And the continuous time version, n is kind of lost, right? I mean, it's, you've taken an n goes infinity limit to get the continuous time version.
So n goes to infinity. Okay, I missed that.
Yeah. I mean, asymptotically, the strategy is not time varying, right? I mean, you're allowed to have a controller that kind of looks at the time left on the clock and then, uses that. And, it might only play bold kind of near the end, the way hockey teams do. But at least here, when everything's zero mean, and the drift of the Brownian motion or the diffusion is always zero, then it's not advantageous to do that. So, on some level, the length of the time horizon doesn't really matter. Your strategy is always just determined by whether you're above or below the threshold.
If you see a similar sort of thing in dynamic programming or that kind of setup where your action space, you have a timid or bold action, for example, and you're trying to maximize your reward, like in a Markov decision process or something.
You're asking if I've seen papers about that, or just?
Well, I'm just wondering if this bang bang control happens in more, in more broader settings even than the ones that you described. Just fairly generally, this is usually, Brownian motion is very special. So I wasn't sure if you just had some sort of nice process, any kind of nice process that you would get this kind of result.
Right. I mean, I guess, so on some level, I mean, there's a continuity argument here, right? For large n, the discrete time process is going to kind of behave like this. And so you should get the bang bang thing. So it's not literally tied to the Brownian motion, right? I mean, the discrete time things that are similar to this will behave like this. I don't think it's going to be quite so clean, if you have like, an arbitrary, two arbitrary distributions with the same mean for your gain in the next step, and n is like 10. I don't think it's gonna be quite so clean as just, play timid, play bold, depending on you're above or below the threshold.
Okay.
Yeah.
Cool. Thanks.
Sure. Okay. So let's apply this to coding. So I need to introduce a little bit of notation here, unfortunately. So bear with me. All right. So I'm going to define what I call the McNamara threshold, which is basically just like a threshold that comes out of his theorem. Okay. So for a given error probability, that's the probability that you end up below the threshold. And for a given range of variances, okay, you can ask, what's the largest threshold that you can handle under the optimum scheme, under McNamara's optimum scheme? So the probability of failure is below epsilon, right? So the higher the threshold, the higher the failure probability. So I want the highest threshold so that the failure probability under the optimum scheme with feedback, probably failure is below epsilon. And that depends on the range here of sigma 1 and sigma 2, right? The larger the range there, the more timid bold you can do. I can define that with feedback and without, okay? And both are expressible in terms of the inverse Gaussian CDF. Okay, the feedback one in particular is kind of messy, but it's it's closed form in the end. And turns out that the feedback does better, right? So as you'd expect, the threshold with feedback there's no coding here. I'm just talking about McNamara's problem. Okay, the threshold you can handle with feedback for the same failure probability is higher than without feedback. Okay. So we're going to express all of our results in terms of these thresholds, and it just hides a lot of, kind of busy notation. Okay, so here's the connection to coding. All right, so there's a key lemma here that's going to relate coding performance, specifically the second order coding rate, to controlling a random walk. Okay, and that's going to be a connection between coding and McNamara's problem. Okay, so I'm going to define a controller to be a function that takes a string of x's and y's. Think of it as like the past inputs and outputs to the channel, and then outputs a distribution over the next input. Okay, so you can think of this as a randomized encoder, a randomized feedback encoder, okay, that observes the history and then outputs a distribution for the next input. Or you can think of this as a controller for a random walk that kind of observes information about where the random walk has gone, okay, and then outputs its distribution for the next step, kind of the way like in the coin flipping thing, you pick the distribution, half plus or minus 1 or half plus or minus 2. All right, a controller and the channel together define a joint distribution over strings, right? So F picks the distribution of x1, and then given x1, the channel specifies the distribution of y1, and then the controller specifies the distribution of x2, given x1 and y1, et cetera, down the line. Okay. So here's the lemma. Okay. So I would not really call this lemma new. Okay. It has like very strong precedents in the literature, some of which are listed here, but I've not really seen it written in this way that kind of connects the second order coding rate with the controller for a random walk, which I think is insightful. So let's parse this. Okay, so it says the second order coding rate is the largest alpha right here, such that this whole thing is true. Okay, so it's the largest alpha so that you can find a controller so that in the limit as n goes to infinity, the chance that this controlled random walk here, which is like, a big sum of, like a discrete time martingale, okay, the chance that this controlled random walk ends up below this quantity is less than epsilon. Okay, and, intuitively, you can think of the right-hand side here, nc plus alpha squared of n is like the number of bits that we're committed to send. That's the k parameter, like the number of bits we're sending. This quantity here, we talked about this on Wednesday. This is the information density. You can think of it as like the actual or realized information that gets through. Okay, and so if the left-hand side is less than the right-hand side, then the decoder kind of intuitively ends up short and doesn't have enough information to really disambiguate the k bits, and so it's forced to just kind of guess. Okay, that's the basic intuition here. All right, so to see the connection with McNamara, you just move the capacity term over. Okay. And then the idea is if F outputs a capacity achieving input distribution at each time step, okay, then you can show this term here will be zero mean. Okay, and so now I have basically like a zero mean random walk, and I'm controlling it, and I can potentially control the variance of it, and I have feedback, and I want to minimize the chance that you end up below this threshold here. Okay, and so now you can kind of see the connection to McNamara's problem. It's like a discrete time version of McNamara's problem with kind of a funky distribution over the increment governed by like the variance of this log likelihood ratio. Okay. There's a non-feedback version of this as well. You restrict attention to controllers that don't have access to the past. Okay, then you have a similar second order coding rate characterization. All right, so the big question is, can we control the variance of this quantity here? Okay, can we play with that? If we can, then we can do timid bold games, right? And do something. If not, then, you know, there's nothing really to see here. Let's talk about variance then. Okay, so first of all, background fact. So a channel can have multiple different capacity achieving input distributions, but they all induce the same output distribution. Okay, it's a fact from the KKT conditions. Okay, so now I wanted to find two different variances. So consider this log likelihood ratio here. The mean of this quantity is the capacity. I want to consider the variance of this quantity under capacity achieving input distributions. Okay, I can consider the minimum possible variance of this thing minimized over capacity achieving input distributions. And I can define the maximum variance, again, over capacity achieving input distributions. Okay, and a little bit more notation. We're almost done with the notation here. We'll let P min be the input distribution that is capacity achieving and minimizes this quantity. And P max be likewise the maximizer. Okay, so any capacity achieving input distribution will give you the same mean for this quantity. Okay, but we want to consider the variance. Okay, and they can have different variances. And then I'm also going to define a per input minimum and maximum of the same variance. Okay, and you know, this minimum is kind of less constrained than this one. Likewise for the maximum, so you end up with an ordering like so. Okay, so just different variance quantities for the log likelihood ratio that's that defines mutual information, defines capacity, and that's going to crop up in our lemma. All right, I'm going to assume nu min is positive throughout. This kind of a technical condition that we don't really need to get into too much. And we'll define a channel to be compound dispersion if V min is strictly less than V max, otherwise simple dispersion. Okay, and you know, it's worth pointing out that most channels have a unique capacity achieving input distribution. And for such channels, they are necessarily simple dispersion because there's only one P here. So, you know, the minimum ends up being the same as the maximum. But compound dispersion channels exist. So here's one example. We'll see others later. Okay, so this is a 6x3 example, 6 inputs, 3 outputs. It's basically 3 symmetric channels pasted together. Okay, and again, each of the constituent channels are symmetric. Okay, so for this 3x3 channel, a uniform input induces a uniform output and is capacity achieving, and the capacity is like log of 3 minus the entropy of one of these rows. Likewise, for this 3x3 matrix, uniform input gives a uniform output, is capacity achieving, and the capacity is log of 3 minus the entropy of one of these rows. Okay, so now we can choose P and Q to equalize the entropy of the rows. Okay, so we choose P and Q so that the entropy of this 3-point distribution is the same as the entropy of this 2-point distribution. Okay, and then when you do that, then you have 2 capacity achieving input distributions, or actually a whole continuum of them. Right, so uniform over the first 3 rows is capacity achieving. Uniform over the second 3 rows, or the last 3 rows, is also capacity achieving. Any convex combination between the two is also capacity achieving. Okay, but the spread of the information density is higher here. Okay, because the range of, you know, the ratio of this to this is I guess bigger than Q to 1 minus Q. Okay, so if I put, you know, all my input mass on the first 3 rows, I'm capacity achieving and I have maximum variance. And if I put all my mass on the last 3 rows, I'm capacity achieving and I have minimum variance. Okay, so these examples do exist, compound dispersion channels. This example is, clearly contrived to illustrate the point. We'll see that many more examples arise when you consider cost constraints later. In fact, on some level, every channel is compound dispersion when there's a cost constraint involved. And we'll see that later. Okay, so theorems. So let's start without feedback. So Strawson in 62, as I mentioned earlier, showed that for any DMC, the second order coding rate satisfies this. It's the McNamara threshold. Obviously, Strawson did not phrase it that way because McNamara's paper came later. But in terms of our notation, okay, the non-feedback second order coding rate is just equal to the non-feedback McNamara threshold. Okay, and you don't prove it this way, but the intuition, I think, in terms of what we covered is reasonably clear. If you can kind of break through all the notation in this lemma, right? Without feedback, the second order coding rate is the largest alpha, so that I can find a controller, a non-feedback controller. Okay, so the chance that this random walk ends up below alpha squared of n is less than epsilon. Okay, so that's just like a discrete time version of McNamara's problem. We're interested in the large n limit, so it should kind of behave like the continuous time version. And so per our earlier conversation, the optimum strategy should be to use P min if you start above the threshold and P max if you start below. Okay, and that is the optimum strategy. And again, this is not the way you prove it, but this is the way to understand it, I think, in terms of what we've discussed so far. All right, so here are the new results then. So first of all, we can show that for any DMC with feedback, the second order coding rate is at least McNamara's threshold with feedback. And as we noted earlier, this is strictly bigger than McNamara's threshold without feedback for a compound dispersion channel. And that is, as we just saw on the previous slide, that is the second order coding rate without feedback. Okay, so an immediate corollary is that feedback improves the second order coding rate for any compound dispersion DMC because of that inequality right there. Okay, so let me go through the proof at a very high level, like one slide. So all of our proofs go back to this key lemma. Okay, so we just always reduce the second order coding rate determination to this key lemma, and then try to relate it to McNamara's setup in one form or another. Okay, so here I want to plug in this McNamara's threshold with feedback. Okay, and then I want to exhibit a controller so that controller of this zero mean random walk, so that the chance you end up below the threshold is less than epsilon. Okay, and we have a template for this, right? Because we know McNamara's controller is optimal in the continuous time limit, so we can kind of like apply that at finite n, and then try to prove that it works in the limit, right? So we choose our controller to be capacity achieving for every possible state. In that case, this increment is zero mean, because this log likelihood ratio is equal to capacity in mean. And we select the bang bang F. Okay, so we use the capacity achieving input with minimum variance if we're above the threshold, and we use the one with maximum variance if we're below the threshold. Okay, and then you just try to show convergence to McNamara's setup, and then like invoke his characterization of the performance of the bang bang controller and the Brownian limit. Okay, and there's some technical issues here because there are theorems that show convergence of discrete time martingales to Brownian motion, but or controlled random walks to controlled diffusions, but they have some technical assumptions that aren't satisfied here. You gotta work around. Okay, but that's the key idea. All right, and we call this timid bold coding. Okay, so the idea is you have like different coding schemes, right? And some are kind of riskier and some are safer, and you use you monitor the progress of the communication using the feedback link, and as long as it's going well, you use the timid scheme, and then if it looks like errors are likely, then you kind of switch to using the risky scheme, the bold scheme. Okay, you throw Hail Mary passes toward the end of the block length. Okay, if this communication is just not working. All right, so let's go back to our running example. So Strawson determined the second order coding rate without feedback, and that's in red here. And now the blue is the achievability result that we have. So it's the lower bound on the second order coding rate with feedback, and you get an improvement, over the entire regime, although it kind of shrinks at the boundaries. the gap between the two kind of disappears in the boundaries. All right, so this raises the question of when feedback helps. So for what set of DMCs does feedback improve the second order coding rate? Both the set and its complement are non-empty, right? Because we know compound dispersion channels see an improvement, and we saw in the beginning that symmetric channels do not, right? So, it's a non-trivial question, right? Both sets are non-empty. So we can answer this, and we show that it's maybe the most pessimistic answer possible, which is it's only the compound dispersion channels for which you see an improvement. Other asymmetric channels, they're not compound dispersion, i.e. they're simple dispersion, do not see an improvement. And the way to show this, again, the first step of all these proofs is to go back to this lemma. So you want to show that if the channel simple dispersion, okay, then if the channel simple dispersion and the encoder is allowed to be a feedback encoder, then you can't beat the McNamara threshold without feedback, right? That's the goal. So for any feedback encoder, the chance that you end up below McNamara's threshold without feedback is at least epsilon. All right, so the main step of this is to use a reduction to essentially a constant composition code. And the constant composition reductions are often very tricky in feedback situations. But in this particular context with the second order coding rate, it's possible to do something like a constant composition reduction. And Fong and Tan in 2017 invented this method that we use. They applied it to a slightly different context. But the bottom line is we can restrict attention to F so that the X process is empirically capacity achieving with high probability. Okay, so the empirical distribution of the X string, with high probability is capacity achieving. And if the channel simple dispersion, okay, and the X process has an empirical distribution that's capacity achieving, then the sum of the conditional variances of these terms here, given the past, is fixed. And so there's just no timid bold game to play here because, at one particular time, you might be able to kind of choose a high variance or low variance thing, okay, but over the course of the entire block, it's all got to add up to the same thing in the end. So all you're doing is kind of moving the variance around within the block. You're not really controlling the absolute amount of variance that you're seeing in this random walk, okay? And once you have the sum of the conditional variances of these terms given the past is fixed, then it's like a straight shot to use martingale central limit theorems, and that's that. All right. How much does feedback help? Okay, so for compound dispersion DMCs, we saw that the second order coding rate can be improved with feedback. In fact, it is improved with feedback. We have a lower bound on the second order coding rate. You can ask, is this tight? Can we prove an upper bound on the second order coding rate? So we have an upper bound that is sometimes tight, but not always. The upper bound is very similar to the lower bound, especially when I choose very strategic notation like this, that kind of looks the same. So remember, this is the minimum and maximum variance over input distributions, whereas nu-min and nu-max is the minimum and maximum variance over inputs. Okay, so the spread between V-min and V-max is smaller than the spread between nu-min and nu-max. Okay, so we can sandwich the second order coding rate between the McNamara threshold where you have this smaller range to play with and where you have this like wider range to play with.
Aaron, can you remind us, please, the difference between beta and alpha? I forgot what beta is.
Beta is the second order coding rate. Beta is the 1 over square root of n back off to capacity. And alpha is just a dummy variable I'm using in the lemma.
Okay.
Alpha doesn't have any intrinsic meaning. Yeah. Okay, so this is actually the most interesting proof of the bunch. So let me say a little bit about this. Okay, so we want to prove an upper bound now in the second order coding rate that's very similar in spirit to the lower bound, but with different parameters. We go back to the lemma, right? It all goes back to this lemma. So we want to show for any feedback controller, the chance that you end up below McNamara's threshold with this wider range of variances is at least epsilon. All right, so we start by weakening this, the key lemma by putting the capacity achieving output distribution here in the denominator. And as I've written it here, it's not obvious that this is a weakening. Like if I just replace the output distribution induced by F with the capacity achieving output distribution. It's not obvious that going from here to here, is a weakening, but it is. You can write this bound, you can write the key lemma in different ways, and one of the other equivalent ways makes it clear that this is a weakening. So we do that. So just take my word for it that that's a weakening, okay? And this weakening is almost surely loose, okay? So I think we've given up something going from here to here, okay? What follows after this, I think, is tight, but going from here to here, I think we've given up something. So essentially, the F has no incentive to be capacity achieving anymore, okay? Because the mean of this thing is C, regardless of what mean of this thing is C, regardless of what F does. So that's what we've given up. Okay, so at this point, we have the problem of controlling this random walk with that zero mean, and has a conditional variance for the increment in this range. You can prove that the variance of this thing is in this new min versus new max range. So this is just like a discrete time version of McNamara's problem, right? It's a straight up discrete time version of McNamara's problem. We know the optimum controller for McNamara, so we should be done here, right? But there's a technical hitch, which is that McNamara characterized the optimum controller in continuous time, and this is a discrete time setup, right? Now we're interested in is the limit as n goes to infinity, and there are convergence theorems that show convergence of discrete time random walks or discrete time martingales to continuous time diffusions. Okay, but those theorems all assume that your discrete time process is like very nice and well behaved and controlled and stuff, and we can't assume much of anything about this process. F could be some arbitrary controller, right? Some arbitrary encoder. We really have very little control over it. So we can't just, directly invoke McNamara's theorem. So to get around that, we use a completely different theorem of Strawson. Okay, so in an unrelated paper a few years later, Strawson proved this martingale embedding result. Okay, so here's the statement. So if S is square integral martingale starting at 0, then you can couple it to a Brownian motion with stopping times. Okay, so that the Brownian motion evaluated at the stopping times is equal in distribution to the martingale. Okay, so any discrete time random walk, if you will, any square integral martingale can be viewed as a Brownian motion kind of stopped at various stopping times. Okay, that fact already is interesting, and often when people quote this result, they kind of stop there, put the period there. Okay, but actually there's a second part of the theorem which is particularly important for us, okay, which is that not only is this true, but in addition, the expected time between the stopping times, okay, is equal to the conditional variance of the increment of the martingale given the past, okay? So here's how we use this. So, in our original setup, F is controlling the variance of this martingale, the conditional variance of the next step of the martingale at each time step. Okay, by Strawson's embedding, I can instead view F as picking stopping times in a Brownian motion, right? So I can just view my my F rather than picking these variances. I can view it as picking these stopping times, all right? And actually it's picking the time between the stopping times, or the expected time between the stopping times, right? That's kind of equivalent to choosing this variance. Okay, so the controller picks these stopping times, okay, and it's also controlling in particular the kind of mean time between these red points. And then using the scaling properties of Brownian motion, what I can do is kind of compress or expand, okay, so that all of these stopping times are about equally spaced and the process kind of runs faster, okay, between these longer epochs, all right? And now the controller is essentially a feasible controller in McNamara's setup. Okay, if you view now the controller is sort of controlling the instantaneous variance of the Brownian motion, right, then now we're back to McNamara's continuous time framework. Okay, and our controller only adjusts its variance at these stopping time epochs, whereas in McNamara's framework, it can choose, it can vary the variance however it wants to, arbitrarily, but that's okay. We just want to argue that the F that we have, right, is no better than McNamara's, which is what he proves. All right, so you go through all this, you get an F that's nearly feasible for McNamara's problem. There's kind of more technical issues to work through, but that's the key idea. And then you can just invoke McNamara's optimality result, and that's how you prove this. Okay. So we're nearing the end here. Let's go back to our running example. So for this particular example, new min equals v min and new max equals v max. Okay, because like you know, the input with the largest variance is any one of these three. Okay, and v min corresponds to a uniform distribution over those three inputs. All right, so you don't get any extra variance by just finding the single input with the largest variance. Okay, and likewise for v min, or likewise for v max. Okay, so for this particular example, these quantities are equal, and so the upper and lower bound coincide, and so this blue thing, this blue curve, is in fact exactly the second order coding rate with feedback for this channel. It doesn't always happen. Okay, you can construct compound dispersion channels where the upper and lower bound differ, but for this particular example, they're the same. Okay, and let me comment on the example now. So this is clearly a contrived example, and it might lead one to think that this is a very niche phenomenon that only crops up with like these really weird, you know, contrived channels. And in fact, I'd argue it's applicable much more widely once cost constraints enter the picture. So this is my last technical slide, the second to last slide overall. Okay, so I'll explain this in terms of the Gaussian channel. So just consider a straight up AWGN, the power constraint of P, noise, additive noise. Okay. So asymptotically, there are two different input distributions that you can use that are capacity achieving. If you think of it in terms of single letter distributions, there's only one, it's the Gaussian input. Okay, but if you think over blocks, okay, there's actually two different distributions that you can use. You could choose your code words to be uniformly drawn from the sphere of radius square root of NP. That's capacity achieving. And the variance of the information density you can compute. All right. Another capacity achieving input distribution is to choose the code words to be IID Gaussian, 0p, right? In which case, you know, still capacity achieving, obviously, with a different variance that's slightly higher than this one. Okay, so essentially, you know, you have a little bit more variance from the randomization of the input. Like you have like the power here is deterministic, right? It's always the time average power is always going to be P, whereas here it's kind of P on average, right? And that extra bit of uncertainty gives you a little bit extra variance here. Okay, so you know, if you've taken a Digicom class, right? So intuitively, this corresponds to like PSK, where you have like kind of a constant power envelope, and this is like QAM, right? So I can imagine, you know, a scheme that like, you know, kind of starts with PSK, right? And as long as communication is going well, kind of sticks with PSK. And then, you know, if it looks like it's not going well at the end, then, you know, the Hail Mary pass is like you switch to QAM, right? So this is kind of ongoing work to see whether that, you know, that very clear intuition that has, you know, some basis in these theorems, like actually translates to, you know, anything kind of meaningful or useful at all in practice, and we shall see. But I'll point out that like this is not unique to the AWGN. Really, like any DMC with a cost constraint that's active, meaning that, you know, the imposition of the cost constraint forces you to change the input distribution, is going to exhibit a similar phenomenon. You can choose your code words IID, all right, or you can choose them like constant composition, right, and you're going to see a slightly different variance in this log likelihood ratio between those two cases. And so you can, in principle, then do timid bold coding with feedback, and, you know, maybe it's useful. All right, so let's wrap up. So here's the grand conclusion for both talks, part 1 and part 2. So how does feedback improve block coding performance in point-to-point channels? So classically, we know there are these 5 mechanisms, right? You can exploit channel memory to predict the future. You can learn the channel law, opportunistically vary the decoding time, opportunistically vary the power, increase the effective minimum distance, and now to that list, we can add use timid bold coding. All right, thank you.
Thanks a lot, Aaron. This is very interesting. So are these recent results?
Some of the citations were 21, so.
Yeah, well, yeah. So I have a general rule of like, you know, I cite the journal version of a paper if it's available. Otherwise, I cite the conference version. And so every piece of work kind of gets like a a year update when that happens, right? Like when the journal version comes out, suddenly all the dates become recent. So this was like a very long ongoing project, to be honest with you. As I mentioned on Wednesday, it kind of started with a goal of proving that the sphere packing bound was tight with feedback. And I started that, back in graduate school, really. And then when you're in trying to prove the sphere packing bound was tight, I was trying to articulate like what are we trying to exclude, like just in words, like what are we trying to rule out, like what kind of behavior might happen that we need to show doesn't happen or is not productive to happen. And the best thing I could come up with was that somehow like the encoder might change its input distribution in response to what the channel is doing, and you got to rule that out as a useful thing for the encoder to do. And so we tried to rule that out as a useful thing for the encoder to do. And then, one thing led to another. And then, we kind of came up with a regime where actually it is useful for the encoder to change its input distribution in response to what the channel is doing, like through the, timid bold idea. So I think the simplest form of timid bold coding appeared at ISIT 2014. So that's, quite old now. And then a couple of years ago at IC 2018, we were able to kind of work out the details of the full scheme with all the diffusion analysis and so on, and then prove theorems 2 and 3 also. And then this bit about how the AWGN is in some sense compound dispersion and DMCs with the cost constraint or compound dispersion. I mean, this is very recent. In fact, we haven't published anything about this yet, so we're still actively working on this. So it's a big spread of stuff.
Good. So we have time for questions if anyone has questions. Don't be timid, be bold.
People.
I have a comment.
Yeah, go ahead.
Yeah, so what you said about how, feedback actually helps when you introduce the cost constraints is very interesting to me, because, I mean, we observed a similar or related thing when you introduce cost constraints, if something changes in a wired-up channel setting. So that happened quite recently, and I think that there is some relation. So, so the capacity for wired-up channel is usually, I mean, you just need one auxiliary, right? You have this IUY minus IUZ if Y is the output to Bob and Z is the output to Eve. Now, if you introduce a cost constraint, typically in many setups, what happens, right, that you only need to kind of restrict the optimization domain. But for the wired-up channel, it turns out that you have to introduce a second auxiliary. Yeah, and you cannot throw it away because, and it goes into the conditioning. I mean, it just, the formula would look like Y given V minus IUZ given V. And the reason why it happens there, why it turns out to be necessary there, is because it allows you to kind of instantaneously violate the cost constraint so long that you satisfy it on average. Something that you cannot do using just the single auxiliary without the conditioning, without this time sharing. Right. So I'm wondering if there's a
yeah, there could be a connection there. I mean, at first blush, this sounds more reminiscent to me to like a Shalkwick-Kylith kind of thing, where you sort of like intentionally violate the constraint in some situations in order to kind of allow you to, I mean, you kind of save power intentionally in some situations so that you can kind of have it then when you need it in other situations.
Yeah.
In my mind, this phenomenon is a little bit different in that, like, here, like if I choose my code words to be IID standard normal, it's like I'm always kind of in expectation satisfying the power constraint in the next step. Yeah. Right. It's just that there's more spread.
Yeah.
Right. So it's kind of maybe one step removed from from what we were talking about. But yeah, but I mean there might be an interesting connection for sure.
Yeah. Yeah, things change with those power constraints. I mean, you can prove the two auxiliary formula for the case without a power constraint as well, but you usually just remove it by picking the conditioning that maximizes capacity.
I see.
Right? So if you have this V, you would take, V to be whatever, V star that makes capacity or secrecy capacity largest, but you cannot, it's funny that you cannot do it without, when you have, we have like a counterexample where this gives you a strictly lower rate. So yeah, cost constraints are, they have an impact on those types of.
Yeah. I mean, a similar thing can happen, if you have a cost constraint and you look at like no feedback, consider like the second order coding rate with a cost constraint, right? So there, like, you could just have two regimes, so with half probability, you kind of use low power, with half probability, you use high power, right?
Yeah.
And then, you can kind of block the strong converse from holding, by playing that kind of game.
Yeah.
So another maybe related question, not
Yeah.
to wiretapping, but maybe another kind of security problem is that, do you think like this, the time and bold coding would be useful for covert communication because for me, there's the relationship with the square root of n, the second order kind of, where you want to hide that you are communicating. So it's not the rate that you...
So, okay, so by covert communication, you're in a situation where you want like an eavesdropper to not even tell whether communication is happening or not, and so you can fit in like square root of n code words.
Yeah, exactly. Yeah. I'm just wondering because if this kind of a coding would be helpful there.
Yeah, I don't know. I mean, you kind of need feedback for timid cold to even really be a thing. I guess one question is like, is there a connection between the second order coding rate and covert communication beyond just the possibly coincidental, square root of n appearing, in both of them?
Yeah, I wish Mathieu was here; he would comment. But I'm just making more like a structural observation because I know like the second order rate is kind of I don't know.
Yeah, I mean, here you have exponentially many code words, right? It's just that like your number of code words is like, 2 to the n c plus square root of n something, and you're kind of like playing with the square root of n. So, the first order behavior, obviously you're not changing. That's just governed by the capacity. Yeah, obviously the covert communication is a completely different ball of wax, right? I mean, the total number of code words is growing quite slowly with the block length.
Is there a notion, covert communication, of how kind of close you are to getting caught? I mean,
I don't know. I haven't really worked in that area, so I don't know.
Yeah, because then I can imagine how, like timid versus bold, do you have any knowledge, right, of how close?
Right.
Actually, that would be very interesting because it's like when, my colleague Amina always mentioned this example. It's like in movies, in old-time movies, when you're using the phone and the police is trying to track you, right? Yeah. They want to keep you talking because if you cross a threshold, then they can track you.
Oh, okay.
Yeah. You hang up, right? So
we should model that.
Yeah. So it could be,
Yeah.
No, it's an interesting question. I think the covert communication angle is quite curious.
But I think it's mainly the fundamental question is, which I don't know if there is a link between the second order and the covert communication capacity. That I don't know. So
yeah.
Good.
Yeah,
so thanks again, Aaron. This was very interesting. So I'm hoping we can have you more on the channel. We talked, and in future you talked about other work that we can have you. That'd be very interesting. And I hope also to continue this back to the basics series also with more fundamental topics in information theory. Yeah. So thank you for the invitation. Thank you for organizing this seminar series. It's great. I really enjoy it. Thank you, everyone, and have a good and safe weekend. Bye-bye. Take care. Bye-bye.